And hello everyone, Paul here to show you how to identify rocks. What I'm about to do assumes two things. First of all, it assumes that you have either collected from me or have delivered to you those boxes of igneous, sedimentary, and metamorphic rocks. So you're going to need those. And it also kind of assumes that you have watched the lectures on igneous, sedimentary, and metamorphic rocks, so that when I say igneous texture, you have at least heard those words before, right? This whole thing will go much better for you if you watch those lectures. So if you haven't, go ahead and watch them. Okay, so as we know, there's three different kinds of rocks: igneous rocks that form from molten rock. There are also sedimentary rocks that form either from sediment or from chemicals precipitating out of seawater or water. And then there's also metamorphic rocks that form by applying heat and pressure to pre-existing rock and changing it into something else. And so in this video, we're going to learn how to use this grid to identify a few characteristic samples of each of these three different kind of rock. If you want to be a geologist when you grow up, you will take an entire class in igneous rocks, an entire class in sedimentary, and an entire class in metamorphic rocks, along with an entire class in minerals. So obviously there is a lot more here. We are just scratching the surface. So let's begin with igneous rocks. So remember that igneous rocks form from lava or magma that cools to make a rock. Okay, and there's two things that we really worry about with respect to igneous rocks, right? The first is texture. Okay, and texture is over here on the chart, and texture refers to how big the crystals are in the igneous rock, right? We have a few different words that we use for it. Phaneritic, aphanitic, glassy, vesicular, and porphyritic. So this is texture over here too. And so phaneritic means that you have crystals that you can see with the naked eye. You look at the rock and it is made up of interlocking crystals. Okay, it doesn't mean that you squint and you see a crystal. It means that the rock is entirely made up of interlocking crystals. Okay, phaneritic rocks, as we know from the lecture, cool slowly and they generally cool underground. Aphanitic rocks, on the other hand, cool quickly, and there are no visible crystals, right? You look at it, you might be able to squint and see a crystal or two, but generally, no, you can't see any crystals, right? These rocks cool quickly, and generally cool above ground, right? And then in our little continuum of cooling, rocks that cool very fast are said to have glassy texture, right? These are smooth and kind of sharp, and look, well, frankly, like glass. Okay, so these three right here form a kind of a cooling continuum from slow to faster to fastest. Okay, and then we have another one up here, vesicular texture. Vesicular texture has bubbles in it. So what happened here is, as the rock cooled, it also degassed, and so gases came out of the rock. Those gases made bubbles, and those bubbles were preserved in the final rock. Okay, vesicular rocks are also aphanetic, by the way, but we give them their own kind of little texture up here, vesicular. Okay, so that's texture. The other thing that we track with respect to igneous rocks is their composition. Now remember that in igneous rocks, the thing that we're really going to track with respect to composition is silica, right? SiO2, right? And I'm going to go ahead and type that in here. O2. The 2 should be a subscript. but we're not going to worry about that, right? How much silica does the rock have? And as you know, because I know you all watch the igneous rock lecture, right? This is important, right? The amount of silica, as we're going to see, determines how explosive the volcano is going to be. It determines how susceptible the rock is to chemical and physical weathering. There's all kinds of things that the amount of silica is going to control. Okay, and for now, we're just going to worry about generally how much silica does the rock have in it. Okay, if it doesn't have a whole lot of silica, the rock is said to be mafic. Okay, mafic rocks are dark in color. I know one of the big takeaways from minerals was you can't use color to identify a mineral, but you can kind of use the shade to identify an igneous rock. Mafic rocks are dark in color and do not have a whole lot of silica. Now, in absolute terms, they're still like 60% silica, okay, but relatively speaking, not so much. On the other end of this continuum, we have felsic igneous rocks, which are lighter in color. And once again, if you watch my lecture, there's pictures of these, and you'll have a much better idea about what's going on. Felsic igneous rocks are lighter in color, right? And they have a lot of silica. These are 95% silica, okay? And then in between is intermediate, which have, oddly enough, an intermediate amount of silica, right? And so if you know these two things, if you know the rock's texture and you know the rock's composition, okay, that will tell you the name of the rock. Okay, so how do we do this? Well, I kind of break it down here, right? The first two steps are let's eliminate, or the first three steps are let's eliminate some obvious stuff. Okay, first of all, is the rock obsidian, right? Is it smooth and glassy and breaking along a curve? In which case it's obsidian. Most obsidian is dark in color. That does not mean that it's mafic. It's always dark in color, kind of no matter what. So don't assume that just because the obsidian is dark, it's mafic. That's not true of obsidian. Sorry, need a little bit of water there. Okay, so is it obsidian? If so, write down obsidian and get on with your life. Okay, now, when you pick the rock up, is it kind of light? Does it have these visible air bubbles? Is it vesicular, right? That's pretty easy to see, okay? If it does have air bubbles or it's very light, if it's dark in color, it's scoria, that's mafic. If it's lighter in color, it's pumice, that's felsic. So there we get those three obvious things out of the way right now, okay? The other kind of obvious thing is number 3, and that's porphyritic texture. Does it have two different crystal sizes, right? In which case it had two different cooling speeds, right? One slower cooling speed where the larger crystals formed, followed by a faster cooling speed when the volcano erupted or whatever, which gave it a smaller crystal structure, right? So you've got this kind of bimodal crystal structure where you got these big crystals floating around in this what's called aphanetic ground mass, or this matrix of fine-grained rock. If you look at the rock and you see two distinctive crystal sizes, that texture is called porphyritic. We're going to call the rock a porphyry, and we're going to get on with our life, right? I put it across these textures like this because that's kind of how it is, right? It's a combination of this and this, really, okay? Actually, kind of all of them. But anyway, porphyry, right? So first of all, eliminate the obvious, okay? Then, now, if it's none of those, now we're down to these, right? Which I kind of call the big 6, right? I have 3 different compositions, I have 2 different textures, and so I can use those to work out which of these 6 it is, right? So now ask yourself, okay, is it mafic? Is it felsic, right? Is it dark in color? Is it light in color? Or is it maybe equally dark and light, or maybe kind of grayish in color or something like that, right? And so if it's dark in color, it's going to be basalt or gabbro. If it's light in color, it's going to be rhyolite or granite. If it is kind of intermediate gray or equally dark and light in color, it's going to be andesite or diorite. Okay, so ask yourself first of all, what's the composition, right? Then say, okay, what's the texture, right? Do I see large crystals? In which case it's phaneritic, right? So it's either gabbro, diorite, or granite, depending on what composition you said it was, right? If you look at it and you don't really see crystals, then it's either basalt, andesite, or rhyolite. Once again, depending on which composition it is, right? So use the composition. Oh, sorry, didn't mean to do that. Use the composition, use the texture to arrive at a rock name, right? If it's felsic and aphanetic, it's rhyolite. If it's felsic and phaneritic, it's granite, right? So if it's light in color and doesn't have any crystals, it's rhyolite. If it's light in color and has big interlocking crystals, it's granite, right? Same thing here for andesite and diorite, right? And same thing here for basalt and gabbro, right? Except this is dark in color, and this is grayish or intermediate or equally dark and light in color, depending on which one you're dealing with, okay? So, once again, eliminate the obvious ones, right? If it's one of those, just write that down and get on with your life, right? Then use the crystals, the crystal size, and use the composition, right, to arrive at one of these 6 rock names. Write that down and get on with your life, right? Don't get frustrated. Do your best on it. I know this is the first time you've ever identified a rock in your life, okay? Don't get frustrated. Just, do your best on it. Make a piece of paper. Your rock samples have numbers on them. Number them and give me a name, okay? Okay, so that's igneous. Sedimentary is another tab right down here, okay? Remember that there's 2 different kinds of sedimentary rocks. There are clastic sedimentary rocks that are made of pieces of other rock, and then there are chemical sedimentary rocks that happen either biologically, in the case of coal, or when chemicals precipitate out of seawater, okay? Or sometimes fresh water, mostly seawater. Sometimes freshwater though. So that's 2 distinctive different kinds of sedimentary rock. Okay. So here's what you want to do. Pick up the rock and ask yourself, is it made of sediment? Right? Is it, when I feel it, do I see pebbles either, rounded or angular sticking out of it? Does it feel sandy like sandstone? Does it feel like, baking flour cemented together? Or maybe it's very dark and kind of layered, right? Does it feel like it's made out of sediment? If so, it's clastic, all right? And so what you want to do then is just give it a name based on how big the grain is that makes it up, right? If it's a pebble-sized particle, and if you watch the lecture, you know that words like I'm gonna do this. That words like pebble, sand, silt, and clay, to a geologist are size categories, right? And so if it's pebble sized, and you all don't need a number, you intuitively know how big a pebble is, right? If it's pebble sized, then it's either a conglomerate if the pebble is rounded, or if the pebble is angular, it's a breccia, right? And then if it seems to be made of sand, it is oddly enough a sandstone, right? You rub it, it feels like sandpaper, it feels sandy, that's a sandstone, okay? If it's made out of silt, which is about the consistency of baking flour, it is oddly enough a siltstone. And then if it's made of clay particles are very, very small. You can't feel them, okay? Not really. If it's made of clay, it's a shale. And the giveaway for shales is that they're layered. So clay particles are flat. They tend to make a rock that's layered and usually very dark, and a lot of times has fossils in it. Although I don't know if any of yours actually have fossils in them. So if it's not clastic, that means it's chemical, right? It's made out of chemicals precipitating out of usually seawater, sometimes freshwater, right? And the 2 most common here are limestone and chert. Florida is covered in limestone. That's the main rock in Florida. Okay, it's kind of white, frequently has shell fossils. Chert is another rock made in Florida, found in Florida. Okay, telling them apart can be sometimes a little bit tricky, but here's the trick. I know it's a rock and not a mineral, so it doesn't strictly have a hardness, but chert is a lot harder than limestone. You will be able to scratch limestone with your keys. You will not be able to scratch chert with your keys. Okay, so there's kind of a silly little informal scratch test you can use to tell limestone from chert. Limestone will also react to very dilute hydrochloric acid. Chert will not. You don't have any dilute hydrochloric acid. Don't worry about it. Okay, if it's kind of soft and has large interlocking grains, that's rock salt. And then if it's coal, it's coal, right? If it's dark and kind of smelly and kind of falling apart, that's coal. Okay. More specifically, that is bituminous coal. We're going to have another coal here in a minute. That is a metamorphic rock. So anyway, that's the sedimentary rocks. Okay, so look through your samples, write down numbers, write down names. Okay, don't get frustrated if you have problems. Get with me, I'll help you with them. No problem. Okay, if we need to get on Zoom and you need to hold up rocks to the camera and show them to me and say, what the heck is this? We can do that. We can totally do that, y'all. Okay, okay, now, finally, there are metamorphic rocks. These are rocks that begin their life as something else, and through the application of heat and pressure are turned into another rock. Okay, there's two kinds: foliated and non-foliated. Um, Foliated metamorphic rocks have a sort of a layered texture to them. Non-foliated metamorphic rocks do not have that layered texture. Okay, and so when you pick up the rock, look at it and ask yourself, does this have layering in it? If it does, it's foliated. Okay, if it doesn't, it's non-foliated. So look at the foliated rock, right? And let's go from most to least foliated, right? Gneiss has, and once again, watch the lecture, you'll see pictures. Gneiss has these very distinctive dark and light bands running across it called gneissic banding. That's a very high grade metamorphic rock. And it's very easy to recognize. Okay, also easy to recognize is a schist. Schists have very big, very well developed grains of the mineral mica. You can peel them off with your fingernails. They're kind of wrinkly, and they are kind of an intermediate grade metamorphic rock. Phyllite is a lowest grade metamorphic rock. It's usually dark and it has a very shiny surface, because what's happening here is we're beginning to grow the mica grains that are going to be visible here in the higher grade schist, right? And so phyllite is a lower grade version of schist, or a higher grade version of slate, if you want to really tell the difference between them. But anyway, looks a lot like a dark layered rock, but with a shine on the surface because of those mica grains. And then finally, there's slate, which is just a dark, low grade layered metamorphic rock. Right? In the real world, telling a slate from a shale can be tricky, very tricky. Okay, there are ways to do it, but it can be tricky. In your world, the slate is in the box labeled metamorphic rocks, and the shale is in the box labeled sedimentary rocks. Okay, and if you are really very curious about how to tell the difference between slate and shale, let me know, and I will do a little video on that. That might be kind of fun. I might do that anyway. But anyway, so those are the foliated metamorphic rocks. Lower grade down here, and then more heat and pressure, more heat and pressure, more heat and pressure. Okay, there is a whole category of metamorphic rock that are non-foliated. Right, these are metamorphic rocks that do not have the layering in them. And I just noticed I cut off the word grains there. Let me move this over just a little bit. There we go. And so yeah, so these don't have that layering in them. All right, so we have a few. First of all, we talked about bituminous coal over here. Okay, if you apply more heat and pressure to your coal, you actually turn it into a higher grade of coal that is actually a metamorphic rock, anthracite coal. Okay, and then if you start with a limestone and you apply heat and pressure to it, it makes marble, usually kind of white, kind of coarse grain with interlocking grains. And then if I take a sandstone and I apply heat and pressure to it, I make a quartzite. Okay, and I do a whole thing in the lecture about telling a sandstone from a quartzite, right? Because over here we have sandstone. If I apply heat and pressure to it, I make a quartzite. Those can be a little bit subtle to tell apart. Now, in your world, this is in the metamorphic box and this is in the sedimentary box. In the real world, though, you're going to want to look at that under a hand lens and kind of try to tell the difference between them. And the way you do it, by the way, is the sandstone has, rounded grains of sand sitting up against each other. The quartzite has sand grains that have melted where they're touching. And so you end up with these kind of interlocking sand grains in a quartzite, where in a sandstone they're distinct, separate, rounded grains. Need a little bit of magnification to see that, but with a little bit of experience, you can tell it just with your naked eye. And then if I take a conglomerate, if I take this rock here and I apply heat and pressure to it, I make a meta-conglomerate, right? I make a rock that started its life as a conglomerate. Heat and pressure was applied, turned into a meta-conglomerate, right? This is another one of those that in the real world, telling a conglomerate from a metaconglomerate can be tricky. In your world, it's not, but it could be. The trick here is to look for the pebbles that are flattened, right? Because that pressure flattens the pebbles. The other thing, and frankly the more useful thing, is when the rock cracks. When a conglomerate cracks, where is it? There it is. The cracks tend to go around the pebble grains. When a metaconglomerate cracks, the cracks tend to go across the pebble grains. In other words, that pebble cracks along with the rest of the rock. Subtle, but easy to see once you know what you're looking for. And so, like I said, in the real world, even telling igneous from sedimentary, from metamorphic rocks, can be a bit of a challenge. You might go into a new area, you might have no idea what you're dealing with, and now you've got to start identifying rocks, working out a history for the area and all this other stuff, and you're not even sure if it's igneous, sedimentary, or metamorphic, right? So look around, work it out. The good news is, in your world, you've got a box that says igneous, a box that says sedimentary, and a box that says metamorphic. So you don't have to worry about that initial step. If you want to be a geologist when you grow up, you will learn about that initial step and how to do that and what to do. But for now, we'll just concentrate on identifying the rocks that you have. Okay, do not hesitate to get in touch with me if you have any questions or any issues. Like I said, we can get on Zoom and we can hold rocks up to the camera and I can show you what I'm talking about. If you feel like you need that, I am happy to do it. Okay, everyone take care. Bye-bye.